Now we'll determine the low frequency response of the common source amplifier. Remember that in the low frequency band, the gain falls off due to CC1, CC2 and CS shown on your screen. Their analysis, however, is a bit different from the analysis for CGS and CGD. We are going to make a small signal equivalent circuit, but we'll follow a different analysis technique. So let's first make the equivalent circuit. Here we are. The current source I is opened and VDD and VSS are shorted. CC2 is between RD and RL. Now, the technique that we are going to use is going to reduce your time considerably and give you very accurate results. Now, the first step is to reduce Vsig to 0. Second step is to consider each capacitor separately. That is, assume that the other two capacitors are acting as perfect short circuits. The third step is that for each capacitor, find the total resistance seen between its terminals. Now, when you find that, the break frequency is very simple to write. 1 over capacitance multiplied by the total resistance between its terminals. So now on the left side of your screen, I am going to draw the resultant circuit using this procedure for each capacitor separately. First of all, we have CC1. It is easy to see that the total resistance between its terminals is Rsig plus Rg. They are not in parallel because a condition for two resistances to be in parallel is that both of their terminals need to be shared. We see that one of the terminals is indeed ground, but the other one is not shared. CC1 is between them. So omega 1 corresponding to CC1 would be 1 over CC1 multiplied by Rg plus Rsig, that is the total resistance between CC1's terminals. Notice that the circuit to the right of Rg, that is CS 1 over Gm, the current source, RD, RL, are immaterial because we are only looking at the total resistance between the capacitor's terminals. Now moving on to CS, we see that the total resistance between the terminals of CS is simply 1 over Gm. RD and RL are not going to be included because they are separated from the source terminal by the current source. Moving on to CC2, the resistance between its terminals is similar to the case for CC1. Notice that RD and RL are not parallel because their top terminal is connected to one end of CC2. So, omega 3 becomes 1 over CC2 multiplied by RD plus RL. Also, please don't think that RD and RL are in series. They are not. We are looking at the total resistance between the capacitor's terminals. Similarly, in the case of Rg and Rsig, they are also not in series, not in parallel either. Again, we are only looking at the total resistance between the terminals of the concerned capacitor. Now we have 3 different frequencies. My question is, which one of them is going to be the highest? Usually omega 2 is higher than omega 1 and omega 3 because of the presence of the term Gm. Now using these frequencies, we can write an expression for the low frequency gain of the CS amplifier. This part here is the mid-band gain AM, and the rest is the contribution of CC1, CS and CC2 to the voltage gain. Now we can use this expression to sketch the low frequency magnitude response of the amplifier and identify the highest frequency out of the given 3. That will be FL, because its contribution to downfall of the gain will be higher than the other 2. That task is, however, too tedious. So, what we can do is to distinguish the highest frequency, omega 2, from the other one, omega 1 and omega 3. This means that its value should be sufficiently higher than omega 1 and omega 3. Look at this graph on your top right. This is the low frequency magnitude response of the CS amplifier. Observe that at each break frequency, the slope of the asymptotes to the gain function increases by 20 decibels per decade. Now the separation between F2 and the other two frequencies F1 and F3 is quite visible. However, as we just discussed, this task is tedious. So, when we design our circuit, we design it in such a way that omega 2 is automatically much larger than omega 1 and omega 3. This direct selection of values allows us to bypass this equation. And so, our work is made easy. Now let's look at the procedure. The design objective is to place FL at a specified value while minimizing the capacitor values. Now, as we had discussed, omega 2 is the highest of the three break frequencies. Now we select CS in such a way that F2 corresponding to CS is equal to FL. As for the other two frequencies, F1 and F3 can be 5 to 10 times lower than the value for F2. However, their values should not be too low, as that would require larger values for CC1 and CC2 than necessary. This value 10 over here is what is known as a decade. So if F1 and F3 are 10 times smaller than F2, then we say that they are smaller by a decade.